Hi guys, this is a complete playlist on aircraft systems, so you don't have to go anywhere else or watch any other videos or refer to any other books other than this particular video. In this playlist, I will be covering everything from top to bottom, whatever there is in aircraft systems, all the things that you require for your DGC exam, and the things that you don't even need, but will definitely help you when you go for your airlines preparation or anywhere else in this field. So this playlist will only have aircraft systems. I won't be making a series on principle of flight, electrics, and power plants. I won't make a video on that. I'll be taking live classes. If you guys want to join it, you can just comment down below. I'll take your name. We'll start from there. But this aircraft systems, it will be available on YouTube for free. You can watch whenever you want as per your needs. All right. So this PPT that I have prepared has this particular book in it. I have made shorter and precise notes of CAE Oxford Aviation Academy's Airframes and Systems, and this book itself contains around 30 to 35 marks in your DGC exam. So this becomes a very important part. You need to go through it very carefully. All right. And one thing I want you guys to have is a pen and a paper because I will be discussing things that you will definitely forget if you don't revise it. So be ready with a pen and paper. I'll wait. You go grab a pen, grab a paper, and then we'll start. You can pause the video now, get it, be ready. Now we'll start. Right. I hope you bought your pen and paper. It's really important, trust me. All right. So moving on to contents. So there is a lot, but we'll cover everything as I promised. From structures to fuel systems, everything will be covered in brief, in proper details with concepts, so you don't have to mug up anything. But you guys will have to bear with me because I'm a little slow in teaching because I want everyone to be at the same level. Everyone has have their own pace, so I want to go at the slowest so that I can manage all of the students that I have, right? So in this particular video, we will be covering only structures, right? This is the topic that we'll cover. In each video, I'll try to cover one topic each, but hydraulics and flight control, some chapters are there which are larger, so it might need two videos. But in this particular video, structures will be covered completely, right? So I have a question. Can wings of an aircraft break? Looking at this picture, what do you see? The wings are flexing like crazy. What do you think? Will it break? Will it not break? Of course, it can break, right? So it all comes down to whether or not a particular limit has been exceeded. If this wing has been bent more than it can bear, then it will of course break. But if it's within the limits, then it won't break. How do you find the limit? Is by doing testings. You can see these people here have a wing and there are some strings attached to it, and there is a measuring scale on the left hand side. So these people are doing what these people are doing is they are stretching the wing to its limits and checking if there is any damage. That's all they're doing. So this will give them limits, and they'll give the limits to the pilots, and the pilots can keep the aircraft within the limit. That's why it is very important for us to study aircraft systems, and we'll go through the limits and all later. But for now, we have loads applied to an airframe. What are the different loads that are applied on an airframe, right? So these are the three types of load. We have tensile load, compressive load, and shear load. All right. So I will go in this manner only. I'll give you an overview of what we are going to study, and then I will go in details of each one of them. Like tensile will study, then compressive, and then shear. All right. So these are the three types of load that you'll study. First is tensile load, then compressive load, and shear load. All right. So tensile load is a load which stretches the structural member. So whenever you have a substance or material or wire or a rod or whatever, and if it is being stretched, then the tensile load is being acting on it, right? And whenever I use the term structural member here, it means aircraft's various part, be it the fuselage, the wings, the empennage, the landing gear, whatever, right? So remember this definition very carefully. A tensile load is one which stretches the structural member. I want you to write down this, right? And if possible, or if you want to, you can just make a simple diagram. So this will help you visualize it, right? The next one is, sorry. So a tensile load is the one which stretches the structural member, right? And then how do we counteract that? How do we restrict it? How do we prevent it? So we use ties, TIES. Ties are what we use to resist the tensile load. Like it is being acting, right? It will act. Tensile load will act, right? There will be stretching of substances, materials, but how do we counteract that? How do we resist it? It is by use of ties. And one of the example of ties is stringers. You can see in this, this is an aircraft, and the part of the fuselage has been cut out and placed here. And you can see the lengthwise running member. These are what? Stringers. So these are stringers, and they are also called as ties. Ties is a like a major, like, what do you call it? Umbrella word, and stringer comes under the umbrella. Yeah. So ties are designed so that we can restrict or resist the tensile loads. And one of our example of ties is stringers. Okay. If someone asks you what are stringers, you can tell them they are lengthwise running member. You can see they are running lengthwise, right? This will be the length of an aircraft, right? This is how you will measure length. So stringers are lengthwise running member, and they are there to resist the tensile load. Agree? Agreed? All right. The next type of load is compressive load. Compressive load is a load which shortens the structural members. So it shortens the member. It is exactly opposite of tensile load. So here we have again the same material, and this time the hands are pushing the material together. So it is being compressed. It is being shortened, and that is what compressive load is. And a very prominent example of compressive load that you can think of is landing gears, right? The whole weight of the aircraft is compressing the landing gear, right? So that is where the compressive load is acting. Very simple. You can, if someone asks you, where do you see compressive load in an aircraft? You can just say landing gears. Very prominent example. Okay. And again, as in tensile load, there were ties to restrict it. An example of ties was stringers. Here we have that structures that are designed to counteract or resist the compressive load are called as struts. And one of example of a strut is oleopneumatic strut. Remember these words very carefully. Struts is what we use to resist the compressive load. And example, if someone asks you, give an example of a strut, you can tell them oleopneumatic strut. We'll go in details of oleopneumatic strut in later parts, but for now you can just remember oleo here means oil, pneumatic means air, right? So basically we have a combination of air and oil in the landing gear, which is there to cushion the landing. You might have seen these things move up and down, right, during landings. So we will go in details in the landing gear chapter, but for now you can just remember oil and air. And remember this thing: compressive load is restricted by the use of strut. And what did we use for tensile load? It was ties. An example, if someone asks you ties, it is stringers. Right. Now we have the third type of load, that is shear load. Shear load slides one face over the adjacent face. So we have two face here. two adjacent face here, and they are being slided over each other. And the top hand is moving to the left and the bottom hand is moving to the right. So these faces are being slided over each other. So this is creating shear load. And again, what do we use to restrict or resist the shear load are called as riveted joints. Like if I install a joint over here and these surfaces won't move now, right? Even if I try to pull them apart. So this particular joint is called as a riveted joint. Okay, and you might have seen these kind of bolts in an aircraft on the surface of an aircraft. Generally not in our civil commercial aircraft, but in older military aircraft, you might have seen these kind of dots. So these are nothing but riveted joints. And what is the purpose? To resist the shear load. Right. Now we discussed all three types of load. Again, tensile stretches the structural member, resisted by using ties. Example of ties is stringers. Compressive load shortens the structural member, and it is being prevented or resisted by the use of strud. One of the example of strud is all pneumatic strud, and shear load is one which slides the adjacent face over each other. And one of the example of shear load, um, we don't really need an example, but remember, what do we use to resist the shear load? It is riveted joints. And there is no such example for shear load, so don't worry about that, and it's not that important too. Alright, so now when the aircraft flies, right, so during flight it's not just one of each acting, like it's not just tensile load acting or compressive load acting or shear load. These forces might act together because aircraft is a dynamic body. It it can have various type of force at once. So there is most of the time, always, like a lot of the time, there are all these three forces acting together. So they acting together make their own forces. So tensile, compressive, and shear, when they are acting together, they can make something known as combination loading. So these forces, when they're acting together, they form combination loading. So we have tensile, compressive, and shear load. These three were individuals, but now they're acting together. So they create something known as combination loading. And there are again three type of combination loading. First one is being bending, and second is torsion, third is buckling. You might have heard bending before. Torsion, buckling might be new to you. So these are what combination loading. First of all, we had three types of load, that was tensile, compressive, and shear. But now, since these three forces or loads can act together and form these three types of loading, right? So these are bending, torsion, and buckling. Again, we'll go in details of one, two, three. First is what? Bending. Bending is a very generic term. You might have seen it already, or you might have known what bending is. But in definition, a combination of tension, compression, shear force. See, all three forces are acting here. All three loads are acting here. Tension as outer edge, compression as inner edge, and shear across. So you'll understand better with this diagram. You can see this metal is being bent using these two hands. This is what bending is. But what, where are these loads acting? Where are the individual load that we saw here now? These three loads are acting there in a combination loading. So in bending, we have our tension acting on the outer edge. How? Like just imagine this thing. This is being bent. So the top surface is being stretched, right? And what is stretching? Stretching is nothing but tensile load. Exactly. So tension is being acting on the upper surface. Upper surface is being stretched, and we know that whenever there is a stretching force, it is tensile force. So the top portion or the outer edge is experiencing what? Tensile load. Exactly opposite to it is the bottom surface, which is being compressed. You can see the part is being shortened, right? If I make this thing straight, then the top and the bottom will have the equal length. But now since it is bent, you can see the green line is longer than the blue line. There is not much difference, but it is definitely longer, right? So the bottom part has compressed, top part has stretched. So the top part is experiencing tensile load, the bottom is experiencing compressive load. And shear forces always act across, because this is a metal piece which is trying to split from here. You can see it is being break. So this will become two separate surfaces and they will go in different directions, right? So this is what creates shear force. Right now, where do you see bending in the aircraft? So I have placed a figure here. You can see this is a beautiful aircraft that is coming in for landing, and you can see the wings of the aircraft. It is not a straight, it is bent, and this is not a defect. This is something that is very normal. Again, as I mentioned in the early part of the lecture, that bending is fine, and since until it is in limit, until within its limit. If it's within its limit, then it is fine, right? So you can see these wings are bent. I want you to tell me, where do you see the tension, compression, and shear forces on this? Okay, just think for a minute and tell me, where do you see these forces acting? Where do you see like compression? If I ask you, where do you see it happening on the wing? If I ask you, where is the shear force acting, where is the tensile force acting? Right, just look at the wing for a while and try to guess. Alright, so to make things easier, I have also added this diagram. This exact same diagram, I have inverted it and I have placed it here. This is exactly what is happening in this wing. And guys, remember, this is something very important. You have to pay attention because this has come in your DGCA exam as one of a question in my attempt. So you need to be paying extra attention here, right? So here you can see the wing of an aircraft. It is curved upward, exactly opposite to this diagram. So you can see the compression force will act on the top. This time the compression will be acting on the top here, the tension will be acting on the bottom, the tension will be acting on bottom, and shear forces will be across the structure. Okay, again, if you didn't understand, I'll tell you again. The surface this time, as you can see, first of all, see this diagram here. It is being bent downwards. Now we did what? We inverted the diagram and placed it here, and this is exactly how our wing is looking like, right? This is exactly our wing is looking like this. It is bending upward, right? So the compression would be felt on the top and the tension will be felt on the bottom. Shear forces will be across. So in DGCA, the exam the question was like, in flight, where is tensile force, where is compressive force? Something like this it was. And then the second question or the second part or something like that was key, where is these forces in ground? I think it was just a single question in which they asked, in flight what happens, where do you see these forces, and on ground. So on ground it is like this, only like this, the first figure. On ground is like this only, like the wings are heavy now, so it will bend downwards. So on ground, shear will be on top, compression will be on bottom. Oh, sorry. Uh, tension will be on top, compression will be on bottom on ground, but in air it will be exactly opposite because the wings will flex upwards. So it will be compression on top and tensile on bottom. Shear will be always across. Just you need to flip tensile and compression. You can just imagine this particular diagram whenever you are answering this question. Okay, now we'll move to the next type of load or next type of combination load, that is torsion. Torsion is nothing but twisting, torsion, twisting. torsion, twisting. Okay, so torsion is just a twisting kind of motion. So in this diagram, you can see someone is trying to twist, like you might have seen people twisting the clothes after they wash it, right? So it is exactly the same motion. Torsion is twisting motion. So you can imagine a cloth, or in this case, a wire is here, or a metal piece. It is being twisted, right? So the tension, compression, shear forces you can see here. Tension is at the outer edge, compression at the center, shear across. You can just keep this in mind. You don't have to like forcefully mug this up, but it's fine. It's always better to know it. I don't want you to explain this one because neither do I understand this, nor do I want to make something up. But yeah, it was not mentioned in the books very clearly. Why does it happen like this? But it is like this. So I don't want you to mug this up. Neither have I. So yeah, but the bending part, this is important. This you need to learn and understand properly. Okay, if you forget this, tension is on outer, compression at center, shear across, it is fine. You just need to remember what is torsion. It is a twisting motion. Okay. The third one is buckling. Buckling is very simple. It is when a thin sheet of material is subjected to end loads. Although the definition is not very explanatory, it's very simple. See, this buckling thing, na, it happens only to thin sheet kind of material, right? So you need a thin sheet, like I can imagine it as being a metal sheet, and some very powerful hands are compressing it together. So in this case, you can say, yeah, compressive loads are being acted on it, but buckling is said when you have this zigzag pattern over here. This is buckling, right? So whenever there is a thin sheet of material and it is being subjected to end load is nothing but loads applied to the ends of a material, right? So buckling is when a thin sheet of material, this is important. A material need to be thin, otherwise it will be compressive load if you have a solid metal piece, right? So buckling is when thin sheet of material is subjected to end loads. You can see how buckling actually looks in real life. You can see this engine attachment, whatever attachment this is. You can see how the surface is being wrinkled, right? So this is what your buckling looks like, and this might have happened due to very hard landing, most probably, because again, these materials are very strong, but they can resist a lot, and buckling might have happened just because of a very hard landing, and that shouldn't have happened. All right, so moving on, we have some types of load. We have the three classic type of load, that is tensile load, compressive load, and shear load, and three combination load that are bending, torsion, buckling. In this, bending is very important. You need to remember this. Okay. Now, what is stress? What do you understand from the term stress? Ah, yeah. This is a totally different type of stress, although this is there, but this is not what we are going to talk about today. This is not a psychology lecture. So, stress in terms of physics, the boring stress. This is also interesting. Listen, trust me. So, this is an internal force inside the structural member which resists an externally applied force. I know this definition sounds complicated, but trust me, it is not. See, just imagine what I'm saying to you. Take a metal piece, okay, and apply external force to it, right? The external force I'm applying here is nothing but a force of stretching. These green arrows that you're seeing here, this is the force that I'm applying. So imagine like I've attached something here and attached something here, and I'm trying to pull it with a string. I've attached a vehicle over here, I'm trying to pull it here. I've attached another vehicle over here, I'm trying to pull it here. So I'm trying to split this piece apart. Okay, this is what I'm trying to do. These green arrows are my forces, my externally applied forces. Okay, and Newton's third law, as you know, कि every action has an equal but opposite reaction. So these red arrows will be set up inside the material exactly opposite to it of the same magnitude. So these green arrows is what I am applying force, and the red arrows are what is being felt inside the material. So these red arrows here are what is the simple definition of stress, right? So stress is an internal force. You can see it is an internal force because it is acting internally within the system, right? So it is an internal force inside the structural member which resists an externally applied force. Now you might very easily understand the definition, right? And the unit is Newton per millimeter square. You can just keep that in your mind if you can. And there are two types of stress. First one is tensile stress, another one is compressive stress. Very self-explanatory, but the first one, the green arrows are outwards, so I'm applying a force outward, and the final red arrows are being felt inwards. And this is a tensile stress. The type of stress is defined by where I'm applying force, right? Exactly similar to how it was when we were defining what tensile load. We were saying when things stretch. So in even in that case, we were applying external force, right? So tensile stress is when, how to explain it this? It's very simple now. You can just see tensile load is when you are applying force externally outwards and the tension the stress is being felt inwards. This is tensile stress. This is compressive stress, exactly opposite to it. I'm compressing the material and the internal force are being felt outwards. So this is compressive stress. Very self-explanatory. If you look at the images for a while, you'll know what is happening here. Remember, the green arrows here are external forces that I am applying. Red arrows here are internal forces that are being felt. Okay, now there is a very similar term, uh, strain. Right, again, this is a stress, and strain might also look like this, but these psychology people have stolen our physics words. So, but it is very different. So, strain is when an external force of sufficient magnitude acts on a structure. The structure changes dimension. This change in dimension is termed as strain. See, what happens is you imagine mm, mm, mm. you imagine a material. Let's imagine a spoon, a metal spoon. So if I try to bend it, right? If I try to bend it, you need to imagine a metal spoon, okay? First of all, a steel spoon, you might have seen it. If I try to bend the spoon, right, with my hands, and the spoon might just bend a little, it will bend, and then if I release the stress, it will come back to its original dimension exactly as it was, right? Again, if I try to bend it, it will bend. If I release the stress, it will come back to its original direction or dimension, exactly as the spoon was. So this is called elasticity. It is a property which a material inhabits, so it can return back to its original dimensions without any change, right? But in the case, if I bend it too much, if I bend, a point will come where now if I release the stress, if I release my forces, if I release my hand, it won't come back to its original shape. It will remain bent like that. So that is when you break that elasticity point. Strain exactly happens after you break the elasticity point. So whenever we are talking about strain, it is talking about breaking that elasticity point. That's why it is written here when an external force of sufficient magnitude, right? The magnitude should be sufficient enough to break that elasticity situation. So when an external force of sufficient magnitude acts on a structure. In our case, it was a spoon, and it was sufficient magnitude, so we bend, right? And the structure changes dimension. Now it will make sense, right? If you imagine it with a spoon, it will make sense. The structure changed dimension. This change in dimension is termed as strain. Simple as that, right? So in this diagram, you can also see this was the original metal or material, whatever we had, and now we are trying to uh, apply a sufficient magnitude force. So this was being stretched, and then at one point it is being stretched this much. You can see the original length was this, and now the length is increased to this much, right? So now even if I release these hands, no, it won't return back to this shape. It will stay like this only. It has been stretched. Okay. And mathematically, if you want to know the formula, it is change of length by original length. So this is the change in length this much, because this was the original length and this is how much it has increased. So this is a change of length divided by original length will give you strain. And if someone asks you what is the unit of strain, then tell them no unit, because strain is a ratio. Whenever you have whenever you have same quantities in the numerator and denominator, you never give any unit to it. See, because we have change of length divided by original length, right? We have length by length, so won't be any unit. It will be a ratio. All right. Now the next part. This is what is the relationship between stress and strain. As I told you, they sound very similar, and even in psychology, we have stress and we also have strain. So there is something going on between these two. So Mr. Young, Mr. Young was, I guess, a French or English scientist mostly. So he discovered was if we divide stress by strain, that is a Young's modulus. So basically, he wanted to say that if you divide stress by strain, it will be constant. That's all he wanted to say. Ki stress by strain is a constant, and the constant you can name it with my name, Young's modulus. Okay, so Young's modulus is a constant for a given material within the elastic limit. If the material is within the elastic limit, then the strain and stress by strain will be a Young's modulus, which will be constant. Now, this is what, yeah, in aircraft, in flight, aircraft structural member constantly change their dimension, like as shown here. I will play the video now. Look at what I want you to look at is the wings or the structural member, anything, whatever you can see, has been changing shape, has been changing length and changing dimensions, right? Just look at it. Alright, so in this, you can see at this point, the wings were what? Stretched. The wings were what? Bent, right? And when it has landed, the lift has stopped acting and the wings are returned to the normal original position, right? So the structural members in the aircraft constantly change the dimension. This is what I have shown you, one maneuver or one phase. But if aircraft is doing steep runs or it is climbing, descending, or whatever, it changes dimension constantly in variety of forms. So this is normal. This happens even in the aircraft is pressurized. So it stretches a lot in the air because there is low pressure inside the aircraft body. It is high pressure. So the body stretches, the fuselage stretches. And this is normal as long as it is within the elastic limit. As I told you, remember the spoon ka example. Same happens with the aircraft. If you exceed that elastic limit, it won't return back to its original shape. I mean, it's fine. If the wings are bent, but after landing it is being normal, or if the fuselage is being stretched in air, but after landing it is normal, then what is the point? It's fine. So, as long as things are within the elastic limit, it is fine. Elastic limit is what? Structure will retain to its original form after forces are removed, but if the elastic limit is exceeded, permanent deformation will occur. As exactly same to the spoon Kafanda, if you exceed the elastic limit, it will have a permanent deformation, right? Same happens with the aircraft, stretches, bends, different forces acts, but as long as within the elastic limit, it's fine because when the forces are removed, when the aircraft is landed, this is when the forces are removed. It will return back to its original shape, original dimension, so there won't be any issue. Now, as I told you, I will be discussing about limits. Why do we need limits? We were discussing in the initial part of the lecture. Limits are there so that pilots know what to keep the aircraft within and never exceed it. If they exceed it, some damage will occur, right? Be it a permanent damage or catastrophic damage, anything. So there is a design limit load. The word design can give you an idea. It is in the initial phase when the aircraft is being manufactured. So design limit load. So it is the maximum load which the manufacturer or the designer, the person who is manufacturing the aircraft design, right? So design can give you an idea that this is related to the manufacturer. So the manufacturer expects an airframe will experience in service. The load is defined as load factor. Don't go in detail of load factor. I'll tell you that later. It's a pretty fun thing to know. All right. So the thing is, design limit load is a load which the designer or the manufacturer expects the aircraft will feel or will experience in the service, right? So if I'm making an aircraft and I know it will carry what 200 passengers, it will fly from India to London or places which are far apart, will do a long haul flight, and there won't be any maneuvers or aerobatic maneuvers or steep turns or dives or things like that we won't do. So I know the because I'm making an aircraft for what passenger travel, right? So I know ki it won't exceed a particular limit. I'll set a limit ki don't exceed this limits because this is a passenger aircraft and I'm the manufacturer. So keep it within the limits. So this is what design limit load. I am the manufacturer. I know ki it will be used for passenger service. It won't perform aerobatic maneuvers. It won't do steep runs. Won't do dives. So I'll give a limit. I'll give it to the operator or the person who is buying the aircraft. Ki this is the design limit load. Do not exceed it. Okay. So it's very simple term. Design, so you'll know it is given by the manufacturer. It is a limit load, so don't exceed it. It's there in the in the name only, right? And the design limit load is given in form of a load factor. So there has to be some measurement of it now. Like how do you give design limit load? If you yourself were the manufacturer, how would you give a design limit load? How would you like if it was a length, it was a height, it was a distance, it was a weight, it was a pressure, whatever it is, you can just give it a value, measure it, and give it. But for something like a limit load, a design limit load, you have to be, how would you like, just imagine you made an aircraft, you did the testing was done, and now how will they give you like what, how will they tell? Like it's not measurable. Now. How will you measure it? It's difficult. Huh? How will you measure load? How will you measure a limit of the load? So they come up with that we will measure it in form of load factor. Load factor they defined as lift by weight. In very generic term, the total lift will be divided by the total weight, and it is expressed in multiples of g's. Nothing but if load factor will be like 1g, 2g, 3g, 3.5g, 4g. If you have seen Top Gun Maverick, the first scene there when the aircraft is being tested is this only, is exceeding like 9 Gs, 10 Gs, 9.1, 10.2, 10.3 Gs. This is what they were talking about. It was a load factor, basically lift by weight. If I try to overcomplicate it, but if this is going over your head, just remember this thing: key design limit load ka definition given by the manufacturer. Just remember this: the maximum load the aircraft manufacturer expects the airframe will experience in service, and it is given in form of a load factor. Load factor is lift by weight, and it is expressed in multiples of g's. This is all you need to know. If you didn't understand anything, then just remember these lines. Okay, so now we'll go in details of load factor. You can see an aircraft here. The lift is acting on it and the weight is also acting on it. So this is a straight and level flight, normal flight condition. You are in cruise, right? So in a straight and level flight, lift is equal to weight. Obviously, if the lift is more than weight, it will climb. If lift is less than weight, it will descend. But in a straight and level flight, lift will be equal to weight, right? So the load factor, what will be the load factor if I enter a lift, let's say 500, and divided by weight will be same because lift and weight are same in straight and level flight. So 500 divided by 500 will give me what? 1, and it is expressed in terms of g. So 1g is what an aircraft will experience in a straight and level flight. So if someone asks you what is the load factor in a straight and level flight, just tell them 1g. And how did it come? Lift by weight. Lift is equal to weight, so you get 1, right? Now, this is not always the case. You're not always flying straight and level. In case of a turn, if you're turning, what happens is you can see this aircraft. This is the back portion of the aircraft. You can see the landing gears, right? And this aircraft is being tilted to the left hand side. Okay, so all these arrows, I'll explain you. What happens is as the aircraft turns, this is lift. This portion that you're seeing, the yellow arrow, the bold yellow arrow, this is lift, and this orangish arrow is your weight. So in straight level, what was happening? Lift was exactly perpendicular to the chord line, but this time when you're turning, in this case you're turning left, so left will also tilt to the left. How does it happen? See, when you're turning, when you're turning to the left hand side, the left vector left vector, this thing will be divided into two different parts. This always happens. Okay, whenever you tilt a vertical force, it will be experienced in vertical and horizontal plane. Okay, this is exactly what is happening with our lift. It was a vertical force which is now tilted, so it will act in both vertical and horizontal plane. So these dotted lines that you're seeing here are nothing but lift k subvector. So what do you call it? Resultant? No, something was there in your class 11, 12 something. Resultants. No, it was called something. I don't remember it, but just remember this thing. The, in a straight level flight, lift would be like this, right? Lift would be this. This yellow arrow would be here, and will be straight and exactly opposite to it. But now since you have tilted, the left has also tilted. Um, the left has also tilted, and this has resulted in a horizontal component and a vertical component, right? But whatever, whenever you divide something, what happens? It reduces. Individual quantity reduces. If I had one chocolate and I divided it within two people, it will reduce. Like the portion you will get will be less. If I divide it into 10 people, it will be even less, right? So that is exactly what is happening here. If the lift is being divided into vertical and horizontal component, earlier it was in vertical plane only. Now, since it is divided into horizontal and vertical plane, the vertical and horizontal both will reduce. It won't be similar as it was in the first case, right? Since it is divided into horizontal and vertical plane, it will be reduced. The lift in each plane will be, but if you total this, if you add this horizontal and vertical, what you will get is the total lift. It will be the same. It won't have any changes. Exactly the same because if I take 10, if I just divided a chocolate into 10 people and then I collect the same chocolate from 10 people and I join it, melt it and I join it, it will give me what? The same chocolate. That is exactly what is happening here. The lift was in vertical plane. Since it is tilted, it is divided into horizontal and vertical plane, and horizontal and vertical plane will be lesser than this particular uh, bold yellow arrow. Right now, why did I explain you this? Because now, since the vertical plane ka lift is less than the weight, the aircraft will descend. Think again. Earlier, the vertical component of the lift was here and it was exactly balancing the weight because it was a straight and null flight. But now, since the aircraft is tilted, the lift vector has tilted into both horizontal and vertical plane, and horizontal plane is of no significance to us as of now, but the vertical plane has reduced, obviously because it is divided into two parts, right? This and this. So this has reduced and this is not balancing the weight, this portion, right? So the aircraft will go in which direction? One force is this much, little bit upward, and another one is this one. So the aircraft will go down, right? And so whenever you're turning, in this case you're turning to the left, the aircraft will start to descend. Yes, this actually happens. People who are flying, they'll know, yeah, this happens. But this, you cannot let it happen, right? If you're turning, which you have to do a lot of the times, you can't stay in air flying in the same direction all the time. You have to turn. Does that mean you'll be descending constantly and then you have to climb again? No. What you'll do to counteract this is you will increase your angle of attack. So people who haven't studied lift or principle of flight might not know it, but remember this thing: whenever you have to increase lift, you have to increase. You can do a lot of things, but one of the things that you can do is increase your angle of attack. Angle of attack and all, we can go in details in principle of flight, but just remember that whenever you have to increase the lift, you can increase the angle of attack. Okay, so in the second picture, what they have done, you can make you can see this thing, the propeller, black part, and now the propeller is more visible. So what they've done is they've tilted the aircraft upwards. They have increased the angle of attack. Means the wings are here, and now the wings are here. So they have increased the angle of attack. Although it's not very clear in this picture, but yep, they have increased the angle of attack. So the lift has increased. Now the total lift has this much. This is the resultant lift. But these two components, these were known as components. It's written here only. So these are two components, right? So what I was saying, what was happening? We were descending, right? How did we stop descent? By increasing the angle of attack. So in this case, we increase the angle of attack. This increased the total lift and increased the total horizontal and vertical component. Same. See, I took a chocolate. I divided into two people. I gave it to two different people, and they were like, "This is small. This is too small. We want bigger chocolates." So what did I do? I asked them give back the chocolates, and then I ordered a bigger one. I ordered a bigger chocolate, and then I split it. And now, even though it is splitted, the chocolates are still in decent portion. Now the kids are happy. This is exactly what is happening here. We increased the lift. We bought a bigger chocolate. We increased the lift, and even if now you're dividing it, now also it is being divided, but now the horizontal and vertical component are in their decent proportion. Now the vertical component is big enough to balance out the weight. Now the aircraft is no more descending. But see what has happened now. Since the vertical component is balancing it, we are not descending, fine. But what do you understand from load factor? It is lift by weight, and lift is now more than the weight, right? Since we have increased the angle of attack and the total lift has increased, it is more than the weight. You take the total lift and total weight. So total lift is now 2 arrows. You can see it is more than the weight. So the load factor will increase, right? If now, since in this case it was like 500 by 500, so it was giving us 1. Now it is what, 1000 by 500, so it is giving us 2 now. So it is 2 G's of forces, right? So this is what is happening in this case. This is all I had to explain, just to explain you load factor is lift by weight, and in this case the load factor in a straight and level flight, the load factor is what, 1 G's. But when you're turning, you have to increase your angle of attack, otherwise you will descend. So whenever you increase the angle of attack, the lift increases, and the lift increases, so your load factor increases, lift by weight. If you want, you can just pause it, read it, although I have explained it much better than what is explained here, but fine. If you want, just take a screenshot, or don't take a screenshot, please make a note. You might have your pen and paper, draw it, write it, whatever. We are almost done with the lecture. There is a few more things that I have to talk about. This is the second thing, design ultimate load. This is again very similar to design limit load. Design means again manufacturer, okay, designer. So it is again given by the designer or the manufacturer, and it is the ultimate load. What do you understand from ultimate? You can look at this picture. This is exactly what comes in my mind whenever I say ultimate. It's like a crazy superpower. It's like in an ultimate form, right? So design ultimate load is what, when you take your design limit load, which we studied earlier. When you take your design limit load and you multiply it with a safety margin, then you get what? Design ultimate load. Design ultimate load is equal to design limit load multiplied by a safety margin. What is safety margin? Safety margin is nothing but a margin, a buffer that is given so that you won't exceed it by any chance. So see what happens. Aviation is based on safety. A lot of things go. A lot of money is being spent on pilot training, so that just so that they can make aviation more safer. It is the safest means of transport, and we want to keep it that way. That's why we always tend to add a buffer to something. So design limit loads was what manufacturer was expecting the aircraft to never cross, right? But we also add a safety margin. We also multiply it with a safety margin so that there is some buffer that is being left with what the manufacturer is expecting the aircraft to uh, experience in service, and the maximum load that the aircraft can bear. So design ultimate load is design limit load multiplied by safety margin, and design ultimate load is what should never ever be exceeded in normal operation. So it can happen in abnormal operation in a very severe case, but it is something that should never be exceeded in normal operation. Okay, so this again is your DGCA exam question. That's why I have written it here. Safety margin is at least 1.5 time, right? So regulations might have set this up. The minimum safety margin should be 1.5 times. So you take your design limit load, whatever it is, in form of a load factor value in terms of G's. You multiplied it now with 1.5 minimum. It can be more than this if you want to make an aircraft more safe, you can add a greater safety margin, but minimum is what, 1.5. So design limit load multiplied by 1.5 times of safety margin, right? All right, so the next part is safe life. Safe life, it's a term, and what does it mean? Again, read the word, it has its own meaning. Safe life, it is the life till which something is safe, right? So I can give a particular number of flying hours. For an example, I take an aircraft, I manufacture it, I tell the airlines that till 2000 hours the cockpit doors are safe, and for 7000 hours the fuselage is safe, for 1000 hours the landing gear is safe. In terms of flying hours, I have given the airlines that after this, I don't take guarantee. You are supposed to either maintain it, replace it, or put the aircraft in overhaul, right? So it is the life till which a particular component is safe. It can be given in flight hours, it can be given in number of landing, it can be given in total pressurization cycles, etc. Right? You can read the definition. All components in the aircraft have a safe life. It is defined as a minimum number of flying hours, landing, pressures and cycle, etc., which an aircraft can handle without any critical damage. In this image, you can see the fuselage is critically damaged. It had happened, and the fuselage just fell apart in mid-flight. So this happened because the safe life of the fuselage was exceeded. So there were damages to the fuselage, and the flight continued. So the fuselage just fell apart in mid-flight. So this was because the safe life was exceeded. Manufacturer told them ki fly for like 2000 hours, replace the fuselage or maintain it or whatever, but they didn't. So after 2001, 2005, or even at 3000, 4000, 7000 hours, it can happen that at some point it will just give apart. It will just fell apart, right? It will just give up. So safe life is the life till which something is safe. Something here means any part of the aircraft, right? And there are two methods of construction. First one is fail-safe method. Second is damage tolerant. Okay, if someone asks you what is the method of construction, there are two methods of construction: fail safe and damage tolerant. Okay, fail safe, fail safe is as the word it is, fail safe. But that does not make sense. If something has failed, how is it safe, right? It can be. Let's just take an example of an airline. I am the operator of the airline, and I'm operating a flight from Delhi to Bangalore, and there is one pilot. There's one pilot who will be operating that flight. Now the pilot fell sick, and he didn't report for flying. Now will the flight cancel? No, the airline will go in massive loss. So we have a standby pilot that is there to come up and work equally well as the first pilot and continue that flight from Delhi to Bangalore, right? That is what it is. One pilot has failed to report, that then also it is safe. Then also the flight will be conducted in the exact same manner. It won't make any difference. So fail-safe is that only. It is based on a principle of redundancy. Means that um, multiple paths, multiple load path in parallel. If one fails, adjacent member will manage the stress till the next scheduled maintenance. Right. So what we do in fail-safe construction is we have two parts that can bear the load equally well if even if one part has failed. So we attach two parts where we need only one, so that if one fails, we don't have to just stop the flight, we just don't have to put the aircraft in maintenance right away, but we can wait till the next maintenance is scheduled, right? But the disadvantage of it is what? It increases weight of the aircraft. Obviously, where you need one part, you are adding two parts. That is why it increases the weight of the aircraft. And then the second method, which is used in modern airliners, is damage tolerant. Damage tolerant is nothing but in this. what we do is the stressed skin or the top layer of the aircraft, the top layer of the aircraft, the aluminum sheet that is the aircraft being covered in, it spreads the load across the airframe so that the load is taken by the skin. We'll go in details of this. I'll tell you. So first we have what fail safe. You can see here there is two different uh, what do you call it? Two metals are attached in parallel one to one another. You can see one arrow. This is a load being managed by one part, this one, and there is this line that you're seeing here. This is what is separating the second part, and this is the second part over here, right? So we have two parallel pathways, right? These lines will be parallel to parallel pathways that are managing the load. So if one failed, this one has failed now, then also the load is being managed equally well by the second part, right? So in normal condition, this is the case, managed by both. In when one part is failed, the another one is managing it equally well. It won't collapse, it won't have any problem. The aircraft can operate till the next scheduled maintenance. This is fail safe, right? Even if this thing has failed, it is still managing the load properly, right? The damage tolerant design is such that the stressed skin, this is the skin, this outer covering that you're seeing, this is the skin, and it is spreading the load across the structure. So it will be damage tolerant. It won't damage at all. Like, this is what they mean. Damage tolerant, it won't damage, right? So just write down the definitions, very important. This and this, you should understand what is fail safe, what is damage tolerant. In damage tolerant, stressed skin spreads the load across the airframe, and the majority modern aircraft uses it. Okay, now next thing is station numbers. Station numbers are assigned to different parts of the fuselage, wings, for means of identifying position during maintenance, right? So you can see this image over here in aircraft, and there are these lines. These are what dividing the aircraft into various small parts, right? So if I had to tell a maintenance worker that something has happened or some damage has happened on a part of the aircraft, then it would be very easy for me to just identify a particular position and give it a number and then tell them ki acha this part has a issue, you go and fix it, because the aircrafts are large, they are very big bodies, right? So you cannot just tell कि वो लेफ्ट वाली सीट के पीछे से आगे जाना and the third window से right side में देखना. That would be confusing, and it can be very confusing for the maintenance crew or or anyone to understand, right? So what we do is divide the aircraft in various small parts and then number them so that we can now assign position to all the parts of the aircraft, right? So what we do first thing here, before dividing it, we do is we enter a zero datum, a reference datum. A reference datum is usually at or near the rows. In this diagram, you can see this line, this particular line here is a zero datum. So this thing from here, you can consider it as a reference, as a zero line, and then you'll number the things that are number it accordingly. Like if this is 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, right? So you have to have a 0, right? Because as a reference, obviously, this is very common. I don't have to explain this. And the things that are forward of the datum, that is, if there is a part or something ahead here, somewhere here, then it will be considered as sorry, forward will be on this direction, right side, right will be always forward. So this is the zero datum, and if I have something over this side of the aircraft, this will be considered as positive. So I'll number it as +1, +2, +3, or it can be in inches, it can be in millimeters, centimeters, whatever, and these will be positive. But if I have something over the left hand side or the aft of the datum, this side, then it will be negative, right? So This is your station number. You assign it to different part of the fuselage or wings for the means of identifying position. During maintenance is called as station number. The reference datum is usually at or near the nose. It can be anywhere, but usually it is at or near the nose. Things that are forward of the datum or to the right hand side of the datum are considered as positive, and things that are left hand side of the datum or after the datum are considered as negative. So if I have to number something here, I'll number it as in -3, -7, -2.5, -8.7, whatever, right? Now, station numbers are also classified into three different parts. First is fuselage station number. So you can see the image. The fuselage is being divided into several parts, and I can identify a position of the window, for example, or uh, anything that is in this plane, right? But aircraft is a three-dimensional body, right? So how will you identify a position on the wing? If I have something at the wing tip, how will I, mm, you know, number it? That's why we have to look it from the top side too. So from top, it will look like this, and we consider it as a wing station number, where we divide the wings into various small lines, and then you can identify the position of the wing tip or the middle part or the near the root, right? This is wing station number. And then there's also a station number given for vertically defining position, that is waterline. This is called as waterline. This is a little different, so you need to keep this in head. Waterline is nothing but when you divide the aircraft in vertical plane, then it is considered as waterline. In this, you were dividing into this plane like this, and this you are dividing into in this plane from top side, you can see, and in this you are dividing into vertical plane, right? So this is your fuselage station number, this is your wing station number, this is your water lines. Okay, now we will start with airframe construction. All right, airframe construction. Airframe is majorly, or as per your syllabus, is made with three different type of construction. There are three different methods by which you can construct an airframe. The first one is called as truss framework type. So you can see the image here. You can see that there are small, this looks like a Cessna or something, some trainer aircraft. So what they've done is they've taken various steel pipes and they have joined it in some geometric shape, and this is called as truss framework. I will go in detail later on. And second is what? Monocoque construction. You can see the image, a hollow cylinder, and in semi-monocoque you have similar as monocoque, just you have these lines. What are these lines again? What are these lines? Can you guess? Yes. The first thing that we consider that we studied. What did we study? It was what? Tensile load. Tensile load is managed by ties, and one of our example of ties is what? Stringers. These are stringers, right? Right. Now I'll go in details of truss framework type. Truss framework type, what do we do is triangular shapes are formed by using steel tubes. This forms a very rigid geometric shape. So we have steel tubes here, and we have joined them in triangular shape. You can find out many triangles here. If you can look closely, you can find out that these shapes are attached in a triangular form. See, there are many triangles here. So they do this to make the surface more and more rigid. Right. So this type of construction is usually used, or is only used in light training aircraft. That's why it looks like a Cessna. So these type of construction are used in training aircrafts. Why? Because they are strong. You want the training aircrafts to be strong, because student pilots, they mess up the landings majority of the time, right? So they had to be strong. And the next thing is, it is easily constructed, so the construction cost will go down, the expenses will be less. This is what your truss framework type construction is. Okay, after the steel tubes, what you do is you add a aluminum alloy. You cover this structure with aluminum. You won't fly this, right? You'll cover this with the aluminum alloy, and you don't use pure aluminum. You use aluminum alloy, and we'll go in details of the material later on. Second is what monocoque construction. Monocoque means single shell. So a shell, if you know, is a hollow sphere. This is what is monocoque. Monocoque means a single shell. So this also looks like a shell, right? Which is hollow. So monocoque, single shell, and it is hollow, right? So in this type of construction, the complete load is taken by the stressed skin. Again, the skin that you're seeing here, this skin takes up the majority of the load, and we use frames and formers which gives the shape to the skin. These uh, these structures that you're seeing here, these are frames and formers, or formers, you can call them frames or former, whatever you like. So these things are there to give shape to the skin, otherwise the skin will collapse, right? So these things, they give shape to the skin, and they stresses the skin, and then the load is taken completely by the skin. This is a DGCA question. In monocoque construction, complete load is taken by, so you have to take skin or stressed skin. Okay. The complete load will be taken by stressed skin in monocoque construction, and the purpose of frames or formers is to give shape to the skin. So you have to just remember these two things. Key again, load is taken by stressed skin, and frames and formers are there to give shape to the skin. Alright, you won't take key frames and former are there for your load taking. No, they are there to give shape to the skin, but the complete load is taken by the stressed skin. Okay, and this thing is rarely used in today's aircraft because we have another thing that is even more stronger, much better. Okay. The complete load is taken by the skin, and slightest damage to the skin can seriously weaken the whole structure. Even if the slightest damage happens to the skin, it can seriously weaken the structure because obviously the whole load is being taken by the skin. So if there is a slight damage to the skin, whole structure suffers it. Okay. The next one that is used by modern aircraft is semi-monocoque construction. Semi-monocoque construction is like monocoque. It has again frames and formers. It has stressed skin, but with this, along with this, it has stringers. These are the stringers, the lengthwise running member that are there to resist the tensile load that we studied earlier. Right. So it is used by modern aircraft. Stringers are what lengthwise running members that helps to convert pressurization load into tensile load, right? As we studied. And along with the stringers, it also has one more thing, that is longerons. Longerons are not shown in this diagram, but here I have attached one picture. You can see these these lines. These are stringers, and the major lines or the lengthwise running member where you need extra strength is called as longeron. This is a longeron. This is a longeron, and these are your stringers. Okay. So you don't need to confuse it again. Not big of a deal. Just remember, in semi-monocoque, we have frames and formers, skin, and stringers, along with longerons. Okay, so this is your semi-monocoque construction, and it is used by modern aircraft. In this, the load is also taken by skin, but some of the load will be taken by these stringers too. So it is not 100% of load or 100% of reliability you are relying on skin. No, as in monocoque, you are relying 100% on the skin. In this, you are not 100% on the skin because you have stringers also, and you have also have longerons for extra strength, right? So in semi-monocoque construction, remember these points, that it has a skin, frames and formers, and longerons and stringers. So the complete load is not just taken by the skin, but it is also taken by the stringers and longerons. And it is used by modern aircraft. Today's modern aircraft use this semi-monocoque construction. Alright, then we have flight deck window. Not much in this. You just have to look at the diagram. You can see these two panels, and then there is a toughened glass, and then there are actually two toughened glass, this one and this one, and between these two is sandwiched a heating element, and a vinyl layer. Heating element is installed so that the windows can be anti-iced. There's a difference between anti-ice and de-ice. We'll go in detail later chapters. But heating element is installed in the flight deck window. There is also vinyl layer. Just be familiar with the term vinyl layer. Vinyl layer is just a flexible layer that you install in the windscreen, and the reason why it is flexible is so that it can absorb impact of a bird strike. If it is able to change shape, if it is flexible, then it can easily absorb a very high impact force, right? So that's why we have a vinyl layer which is flexible so that it can absorb the impact of a bird strike. Heating element is there so that it can anti-ice the windows, right? So there's not much in flight deck window. We have passenger window, again, not much, just a fail-safe design. So you have two acrylic plastic. These are your acrylic plastic. So it is again fail-safe. What do you understand from fail-safe? As I explained, even if it failed, it is still safe, right? Even if it failed, it is still safe. So fail-safe design, you have two acrylic plastic. Even if one is broken or damaged, you don't have to just panic out because there is one more which can equally manage that pressure very easily. Like, then we have wing construction. You just need to look at the images. That's all there is in wing construction. You just have to look biplane, braced monoplane, and cantilever wing. So there are three types of construction. Biplane is what you have two wings. You can see in this image you have two wings. Braced monoplane is this Cessna, in which I'll just go in detail. I'll just look at the image. Now I'll go one by one so you won't get confused. This one is braced monoplane. Oh, sorry, biplane. So now we have wing construction. So there are three types of wing construction: biplane, braced monoplane, and cantilever wing. So biplane, as the name suggests, it has two wings, braced monoplane and cantilever. Will go in detail. So first is biplane. Biplane is highly resistive to bending, but generates high amount of drag. So these are two wings, right? This is wing and this is another wing, and they are connected with a bracing wire. These are bracing wires, right? So they are metal wires that are connected like this, so to give strength to both the wings. Along with bracing wire, there is an interplane strut. This that you can see is the interplane strut, and these structures are very strong. They are highly resistive to bending. They won't bend. Like you've seen the modern airliners that I showed you, they were bending. So, but in this braced biplane, the wings won't bend. They are highly resistive to bending. But why don't we use these design in airliners? Because it produces a lot of drag. There are two wings and there is an interplane strut, so there will be a lot of drag. The drag will go again in details later chapters, but just remember, in biplane it is highly resistive to bending, but we don't use it because it produces a lot of drag. Right. Second is braced monoplane. Braced monoplane, the wings are connected to the fuselage or landing gear via a brace. Okay, this is very interesting. This is the wing. It is attached to either the landing gear in this case, or it might be also attached to the wing. Like you have seen in this image, it is attached to the fuselage, right? Either it is attached to the fuselage or attached to the landing gear. So why to give extra strength, obviously. And the brace, this bold line is important. The brace acts as stud when on ground, and acts as tie when in air. What do you understand from this? Brace acts as stud. Stud is what? That is there to resist the compressive load, right? So when on ground, when this aircraft is in ground, then the wings will be applying a force like this, right? Will be tilted downwards. So this will get compressed, obviously, right? This thing will get compressed. So Now this thing is being compressed and it is resisting the compressive force, so it is acting as what? It is acting as a stud. Like, what do we use to resist the compressive load? It is a stud, right? So it is resisting the compressive load, hence it is called as a stud when the aircraft is on ground. But when in air, the wings will be bent upwards, right? So now this thing will get stretched. Now as it gets stretched, it is trying to resist being stretched, so it will act as a tie, because the tensile forces will be felt in this, and since it is resisting the tensile force, it will be known as a tie, right? As we discussed in the very beginning. In the very beginning, we discussed whenever there is a compressive force and we are trying to resist it, it will be called as a stud. And if there is a tensile load and we are trying to resist it, it's called as a tie. Next is cantilever wing. So in cantilever wing, you use spars, stringers, ribs, and skin to strengthen the wing. See, in this case, you don't have any stud or any bracing wire to hold the wings. Then how is it hanging like this? So what do we do is we insert certain materials inside the wing itself to strengthen it. We don't need any external attachments. We just put things inside the wing and it is being strengthened by that. So you can see in this case, there are these materials, this and this will study are attached inside the wing. So they strengthen the wing itself. You don't need any external attachment. And now, apart from this, what do? We we mount the engine on the wings. The engines are mounted on the wings, and the fuel is also filled inside the wings. So this, what does it do? It helps to reduce the upward bending movement of the wing. See, in flight the wings will be bent upwards, right? As we've seen in the videos and all, the wings will be bent upward, right? As we've seen in the previous part. So what do? We attach the engines on the wing. So now the bending movement upward will be less. And we also do is we add fuel to the wing. So there will be again lesser upward movement of the wing, right? In the construction of a cantilever wing, we have used certain things inside the wing so that we can strengthen it. What are those things? We have the first one is ribs. So these structures that you're seeing here, these ones with holes, these, these are all ribs. I have marked it here. You can see ribs are what? That give shape to the skin. Their purpose is to give shape to the wing, and these ribs also have holes in them. You can see they have these holes in them. Why are they there? The purpose is to lighten the structure. Like if I cut these holes and remove the metal, so it will be lighter, right? The whole leg will be lighter. So obviously you want the aircraft to be as light as possible to so that you can use the minimum fuel to reach from A to B and you can make maximum profits, right? So the ribs are there to give shape to the skin, and there are lightning holes in the ribs. This reduces the weight of the overall structure. And one more thing, you can see the stringers are also here. These are the stringers, right? And the spars. There are two spars. This is the front spar, and this is the rear spar. You just need to remember the names: ribs, spar, stringers, right? And this is the skin. So these four parts they combine together and form a cantilever wing. One more thing is there that when these things are together considered, they form a torsion box. Torsion box is just a fancy name given to a box-shaped structure that is formed inside the wing, which is very, very strong. So you have your ribs, you have your stringers, you have your skin, and you have your spars. These are the spars. The eye-shaped structures here you are seeing are spars. So these things together they form a torsion box, which is very, very strong. Okay, this is also a DGCA question. Okay. Now, this is the last slide, and we have materials used in the aircraft. So there are different materials but these are the four majorly used materials inside the aircraft. First one is duralumin. Duralumin is a aluminum alloy that we are talking about. It is aluminum based alloy, and it is called as duralumin. Okay, I don't know if I'm pronouncing it right, but yeah. So this thing is having a very good strength to weight ratio. Like the strength is a lot, the weight is less. So it is a good strength to weight ratio. Along with this, it is a good conductor. Why do we need a good conductor to why do we need a good conductor in a aircraft? The reason is because good conductors, what do? They pass the electricity very easily, right? So whenever the lightning strikes the aircraft, they can easily pass it and leave it back to the atmosphere. So that's why we need a good conductor. So the aircraft body, the skin is usually made of aluminum based alloy known as duralumin, and it has a good strength to weight ratio, and it is a good conductor, right? Now you cannot just make the whole aircraft out of aluminium, because there are parts that need a lot of strength, like the landing gears. They have to constantly face a lot of compressive and tensile and shear loads. So the landing gears, they need to be very strong. They are made with steel. Steel is although heavy but is very strong, right? So you only add steel to the part where you need extra strength, like landing gear, right? Duralumin, steel, magnesium. Magnesium is also as good as aluminium, or even it's a little less heavy. I think it's lighter than aluminium. So magnesium can also be used to make an aircraft, but why don't we use it? Because it has poor elastic property, right? It is also having good strength and weight ratio, just like aluminium, duralumin, very good strength and weight ratio, but it has poor elastic property, so it does not stretch or compress. Why do we need stretching and compression? Come on, you have to tell this. The aircraft constantly changes dimension, as I told you. As long as it is within the elastic limit, it is fine. But magnesium, it does not stretch or compress that much. So it can easily exceed the elastic limit. If the aircraft slightly the wings bend, so it will come permanently bend and will have a permanent deformation. That's why magnesium is not used for construction of major part of the aircraft, but it is used in the engine gearbox. All right. And then apart from these metals, we also have composite materials used in the aircraft. Nowadays, it is becoming more and more popular. The newer version of the aircraft are using composite materials. They're lighter than aluminium, they're lighter, they're cheaper. So that's why aluminium and magnesium are being replaced slowly with composite materials. There are carbon fiber enforced plastic, and another one is your glass fiber enforced plastic. So carbon fiber enforced plastic is very strong, just like aluminium, but is 20% weight as so carbon fiber reinforced plastic is as strong as aluminium, but is 20% lighter. And then you have glass fiber reinforced plastic, which is very light. It is actually very light, but it is not very strong. So we only use it to make fairings and all. Fairings is nothing but streamlining parts that we add in the aircraft. We'll go in details of fairings later on, but this is the total materials that are being used in the aircraft. There are other materials too, but these are what major materials that you need to know for your exam purpose and in general for your airlines and whatever. There's one question that I have written here. This is titanium is also a good material for aircraft construction. It is light, it has good strength and weight ratio, then why it is not used? You have to answer this question. I'll leave it up to you. You can search it up. You can put it down in the comments if you know the answer. But I'll give you a hint that the metal that we are using here, titanium, has no flaws. It is good conductor, it is good elastic properties, it is light, it is good strength and weight ratio, then also why is it not used? What do you think? Other than being strong, good conductor, and being elastic, what is one more thing that the manufacturer had to consider before using a material in the aircraft? Right? I won't give any further hints. I want you to figure it out by yourself. So go ahead, search it up, and put it down in the comments. So that's all that I have for you in the aircraft systems structure. Well, more videos will be coming in soon. I hope you really like that. You just let me know the feedbacks. If you, what do you think I should improve on? What do you think you liked about the lecture? And what you don't, what you didn't like about the lecture? Were you confused? Did you understood the concept properly? Just put it down in the comment, whatever comes up in your mind, and you obviously answer this question in the comments. And also check out the description. I've added details about the live lectures that you can join, and more videos on aircraft systems will be coming in shortly. I'll try to upload as regularly as possible, but um, let's see. Alright, so bye bye. Have a good day. Enjoy.